Welcome to Longevity by Design, a podcast designed to give individuals access to the leading scientific information in the field of longevity. The ability to add years to your life and life to your years needs no opinion. Join us as we ask science to take the wheel. In each episode, Dr. Gil Blander joins a co-host and an industry expert in the field of longevity, shining a light and getting the answers to the key question: how can we live a longer, healthier life?
Hello, I'm Ashley Reaver, and I'm joined by Dr. Gil Blander. Welcome to Longevity by Design, How to Live a Longer, Healthier Life. We're produced by Insight Tracker, your science-based guide to optimizing your body from the inside out. Our guest today is Dr. Jennifer Elisseeff. Dr. Elisseeff is a professor of orthopedic surgery and director of the Translational Tissue Engineering Center at the Johns Hopkins School of Medicine. Dr. Elisseeff has her PhD in medical engineering from the Harvard-MIT Division of Health Sciences and Technology. Some of her research interests include the use of stem cells for tissue engineering, regenerative medicine, aging, cornea repair, and cartilage regeneration. More specifically, Dr. Elisseeff is examining hydrogels as a scaffold for tissue engineering and is working to develop an artificial cornea. Thank you so much for being here with us today.
Thank you. Excited to be here.
So, Jennifer, we always like to start from the beginning. And we like to ask what drove you to become a scientist? And specifically, what drove you to dedicate for regenerative medicine?
Well, that's a great question. So I would say it really started with a love of nature and a fascination with nature. Seeing plants and animals around, and also I have to say my father was a professor too. He was an engineer working in material science. So I think a combination of all of that was important. Also, I was always interested in medicine. So, how did the body work? So, even though I didn't finish medical school, I did some medical coursework and went to the field of biomedical engineering, where you could have a medical impact, have medical knowledge, but then be connected with developing new technologies.
Excellent. Great story. So, another interesting fact about you that you recently started a biotech company. So first, it will be interesting for us to hear about that story. And second, what was the effect of being part of Bob Langer's lab on that? And specifically for our audience, Bob Langer is a professor at MIT that maybe is the one that the highest amount of patents in the world. And to someone that doesn't know about it, but definitely you need to learn about him. He is the founder of Moderna, which everyone today should know. But that's one company out of, 500. So, Jennifer, to cut a long story short, can you please tell us about your journey of starting your own biotech company?
Yes, I'd like to tell people that I grew up with it, right? So being a PhD student in Bob Langer's lab, it was just all around you, right? And Bob is such an incredibly generous person. And as a PhD student, he let me take his place in board meetings for regenerative medicine companies to talk about my research. So it was just a part of it was a part of daily living, really. It infused everything that you did in the sense that you would think about, how can I make an impact? How can I make people's lives better? What are the challenges, particularly in the field of regenerative medicine, for getting to people?
Excellent. And if we are getting into your case in regenerative medicine, we know when we done the research, we've seen that you spend some time and you work with stem cells.
Mhm.
And to our audience that is not a PhD biology, can you explain what are stem cells and what is interesting about them and what attracts you to work on stem cells?
Yeah, so during my PhD work at MIT, we were building biomaterials that were designed to be a support structure for cells, the basic building blocks of tissues, to make new tissues, right? And when I came to Hopkins about 21 years ago now, stem cells were just being sort of discovered and developed. And Stem cells are interesting because they have the potential to proliferate a lot, and then they can also become multiple tissues. So, for example, adult stem cells that you might find from the bone marrow, they can become cartilage like cells, bone cells, fat cells. And that really, it was thought to be a barrier in the field that how do I get enough cartilage cells to replace your cartilage? Right. And stem cells were a potential solution to that. And we worked on stem cells for actually a number of years, and but then actually shifted gears. So after doing some clinical trials, both for cartilage and a soft tissue reconstruction technology with Kythera Biopharma, we recognized the immune system seemed to be important. And there's beautiful work by Ben Cosgrove and Helen Blau that looked at aged stem cells versus young stem cells. And they found that, well, the aged stem cells, when you took them out of that aged environment, you could rejuvenate them and put them back, and they worked better. So the immune system just seemed to be a potential avenue that was more important, actually, even than stem cells, environment for growing new tissues.
Are there
Interesting.
other places in the body other than bone marrow where we can find stem cells in adults?
Absolutely. They're really stem cells all over. So you have stem cells that are helpful in your skin. So, there's a basal layer, a bottom layer of stem cells in your skin that will divide and produce progeny that make your skin in your gut. You have hair stem cells, muscle stem cells. They're really all over the place. They really provide the spore for new tissue growth. And I'll say that's amazing.
Definitely. And you mentioned that you started, as we said, you started working on stem cells, and then you shifted your focus to immunology and the
Yep.
immune system. So can you explain why and
Yeah. Yeah.
uh,
Absolutely. So, in our clinical trials for cartilage repair, um, we noticed that we actually weren't following that traditional tissue engineering paradigm where the biomaterial scaffold was the 3D framework for new tissue development, but we were actually sort of redirecting the tissue repair process instead. And then our clinical trial with the soft tissue wrinkle filler, we saw some immune cells around the implants that were sort of unexpected. And I decided that I needed to go learn something about the immune system. And I went on sabbatical and into the lab of Melody Swartz in Switzerland. And so I tried to learn some of the language. It's a hard field to go into when you're, when you're new. But I came back to Hopkins, and the president of Hopkins put me on a committee for translation of technology. So how could Hopkins, do more startups and be better at translating technologies? And my co-chair in that committee was actually an immunologist who developed a lot of the cancer immunotherapies. So, I realized that next door to me, I had some of the world's leading immunologists. And so we started using the techniques that they use for looking at what immune cells are in tumors and applying that to tissues. And, one story that really struck me, I was driving between the hospital and our main campus. And I heard an interview with Tom Hanks, who likes to visit veterans and supports veterans. And he was meeting two soldiers that had both lost a limb. And he said one was in rehab for 3 months, and the other one was in rehab for 3 years. And the only difference was that one had an infection. Right. So again, the immune system and its role in repairing tissues, in addition to fighting infections, very interested in understanding how we can them to stimulate.
and if we are talking about immune system and tissue repair and aging, as you said, I have a friend that's always telling me that when he was young, like a kid, he had some scar and it basically got repaired and become new like in a couple of days.
Yes.
and now in his 50s or 60s, it might take like, I don't know, so maybe never. You'll see this car 10 years older than that. So definitely there are some effect on the immune or regeneration of our body related to the age. Do we understand why is it, or it's still an enigma?
I would say we're learning about it. So I'm very excited about some studies that we've done recently where we put in a biomaterial that stimulates repair into a muscle wound. And we put it in young animals and old animals. And in young animals, we get this nice stimulation of the immune profile that is pro regeneration and it's working great. When we put that same material in the older animals, it's not working. And what was really interesting is that you have some baseline inflammation in the older animals, as you might expect, but the injury actually unleashed these new immune profiles that were different in the older animals. And it's actually an immune profile that really actively blocks repair, right?
Mm.
And so I think of this actually now as elements that are lost in translation as we're developing new technologies in our models in the laboratory versus what happens in people. And there are a lot of differences, right? And one of them is aging, right? We don't consider our age in our therapeutic development. Also, things like diet, microbiome, and sex differences, and also comorbidities. Something else might be going on in the body that is impacting a certain injury. So, I think there's a lot to do, and I'm really excited about the concept of combination therapies. So, we have a therapy that might work in young, but if you're a little bit older, you need an additional drug or therapy that sort of addresses those factors that block what we want to see in the case of tissue repair. So I think it's actually a really exciting time. The immune system is important, but then also the way the immune system talks to the tissue. We see that that's not working the same way in older animals. And the other tricky part is that there's such diversity in aging. You've done work or looked into sort of what's your biological age. And even when we look at our models in the laboratory, as they get this diversity in the response. So that makes it even harder then to try and develop a therapy that will work in everyone.
So I think that maybe we'll use the clocks that are now very popular, and then based on that, we'll fit the right treatment for the right person based on his, let's say, biological age.
Right, or potentially even immune signatures, or some signature of the clock and immune profile, and maybe some proteins that may be missing or maybe blocking the repair process.
And the field of regenerative medicine itself has definitely exploded in recent years. Where do you see, or what do you see as the future? What possibilities are you excited about where the field could go?
That's a great question. I'd still like to see more therapies reaching people, right? And really addressing the challenges of, oh, we have this cool science and these cool technologies. Why isn't it reaching the clinic? Right? Can
Mm.
we get it there faster? And I think there's an interesting story with that with stem cells actually. So I mentioned how stem cells were first defined about how they could make all these different tissues. Well, as the clinical trials happened, it became it became obvious that actually they weren't building tissues, but they were enabling tissue growth through guess what? Modulating the immune system. So I think we may develop something in the laboratory thinking we know how it works, and then you get to people in a way. So I think the more we get that experience with translation, of course, doing it safely, we'll be able to learn more about how to do it better.
So I'd like to shift gear and talk about biomaterials.
Mhm.
And I would like to ask you the question about how biomaterial are fitting into regenerative medicine or applications.
Yeah, there are a number of ways that biomaterials can fit into regeneration. I think early on you saw biomaterials as sort of a simple substitute, right? So a knee implant, a synthetic, a hip implant, breast implant. all these things are meant to mimic at least the physical structure and some of the function, but of course, missing the biology. And then as the biomaterials development sort of matured, particularly with tissue engineering or regenerative medicine, we started thinking about biomaterials actually connecting with the biology and really integrating with the body so that then they're actually stimulating tissue repair in addition to sort of fixing the tissue physically the way you might want it to. So they can be used to deliver drugs, right? Maybe to improve formation, and also potentially to serve as, again, a scaffold for cells that are there locally in a tissue or cells that you might add in there.
And I can't, in my mind, I keep repeating just that your dad was a real engineer. You are working with the ultimate material, which is a really cool kind of parallel there. Do you
Yes.
see, yeah, the biomaterials, how they've advanced over 10 years? Or obviously being able to regrow tissue is very cool as opposed to just an implant. But have there been a lot of changes over the past 10 years kind of beyond that?
I would say there are a lot of ways people have modified materials with certain biological signals we think are important. We've actually stepped back a little bit as we've been applying these more sophisticated immunological techniques, saying, like, well, we need to understand actually some of the baseline fundamentals of what happens when a biomaterial is in the body. And the things like the immune response were so overpowering to any of the sort of smaller modifications we make. So that's connected a little bit with our switch to looking at the immune system. But I think we'll get back into modifying biomaterials at some point to really the immune system. So I think we'll see hopefully more biomaterials development, even from the simply the drug delivery perspective.
And any other tissues that influence the effectiveness of the biomaterials other than the immune system?
Absolutely. So you have your local tissue cells. So you have interaction, the vascularity, blood supply. You've got some really exciting new field of understanding fibroblasts. Those are a cell type that were considered to be important. Sorry, I've got a visitor here. For scarring. Um, and I remember in medical school, someone said, well, fibroblasts are like the cockroaches of the body. They just go in quickly and make your scar and clean things up. Now we're understanding that they're actually really sophisticated. And you've got all these different types with all these different functions that contribute to all tissue structure. And we're learning which ones respond to mechanical signals and which ones respond to growth factors and immune cells. So we're learning a lot more about the basic tissue structures.
And I'm thinking about people in my life that have had replacements of some sort of joint. The
Yes.
ones that had an infection, they have had 2 or 3 replacements of the same joint
Yes.
since then.
Yes.
It's yeah, I've never made that connection before. And they're both still in pain, truthfully.
Absolutely. And those factors, having that infection or even some other problem in the body somewhere else can really impede the repair process and really limit the function of the biomaterials. So again, developing materials that are more sophisticated, whether it be antibiotic coatings or some smart materials that can respond and really block an infection, are going to be important in the future.
And do you know if there or do we see any tissue specific immune response
Yes.
of yeah, in one area versus another?
Well, so in our study with Kythera, when we were looking at these soft tissue fillers, we implanted them in tissue that was going to be removed later. So tummy tuck, essentially tissue. And what we saw is the same biomaterial could have different immune cells around it, depending on if it was adjacent to muscle
Mm.
or fat tissue or muscle or just dermis, the lower layer of skin. So absolutely, the same biomaterial can have different responses depending on what tissue it's in, what's the neighbor.
There seems like so many different layers of logic that can go into choosing the correct things.
Yes.
It's definitely an infinite possibility or infinite possibilities that seem
Yes.
like are out there.
Yes, and one
Uh,
thing
it-
that we're even looking into beyond that is feeding mice a high-fat diet. What does that do to the biomaterial response? And we know it changes the immune system, so it's likely going to change the response to the implant. So I think that's really exciting too.
Incredibly interesting. How do you account for all of these things eventually, if you translate this into medicine?
Yeah. Well, this is where big data can be helpful, right? And I think taking an engineering approach, we think of systems, right? So these are all different elements of a system that are working together, right? Essentially keep us alive, right? And if it's muscle tissue, to keep the muscle working and intact. So we think of it more from that perspective. How is the system working to optimize your performance? And each of those different cell types are part of the system.
And I think that's a good segue to our next kind of chunk to talk about, which is senescent cells in general. As your entire system ages, how that can
Yes.
also change these cells. So, why are there more of these senescent cells in aging people or in
Yeah.
people as we age?
So I think I might have a different perspective on senescent cells than what is maybe standard in the field. First, I was lucky to be introduced to senescent cells by Ned David, who started or co-founded Unity that focus biotechnology that focuses on senescent cells. And these cells were, recognized that they don't proliferate, right? But they secrete factors, this senescence associated secretory phenotype or SESP. And these cells accumulate with aging, as you mentioned, are involved in a number of age related pathologies. So we were looking at arthritis, also involved cardiovascular disease, diabetes, kidney disease, you name it, and they've been implicated in it. Um, but they're also important for tissue repair and early development of your tissues. So, why are they good? Why, when are they good? When are they bad? And as we've looked at them in the context of wound healing, they're part of the wound healing, but if they don't get cleared, and let's say if you have an implant that induces fibrosis, we can use our biomaterials to model this.
Mm.
And we see the senescent cells communicating with immune cells. So again, we're back to our favorite topic there. So we've used some model systems and some transgenic models from Mayo Clinic to identify which cell types are senescent. And we see some around vasculature, which I think is quite interesting because I think they're involved with angiogenesis or new blood vessel development. And as we get older, our small blood vessels don't work as well. They tend to be leaky and not as robust. So that's why as you get older, you need to do more interval training, right? Get the blood moving through those little blood vessels. So I think they're a signaling cell in the context of that. And then we also see them in fibrotic regions. And both of those different senescent cell types are talking to the immune system. And again, they're working together as a system to say, we got to get this tissue functioning well. And as you're aging, that gets off. So I see it almost as a byproduct for sort of the system's dysfunction with inflammation with aging, and then also the vasculature problems with aging. So we'll see how it turns out as the field learns more about what these cell types are. But I think we're going to see a lot of movement as sort of new computational techniques develop to identify and understand what they do along with biology models. So we have an hypothesis and an idea of what we think they do. So we'll see what happens.
So I used to work on senescent cells, I don't know, 25 years ago. And time the dogma was that actually senescent cells are there. When we age, we accumulate more senescent cells. And one of the role of the senescent cells is actually to prevent cancer. So when you have senescent cells, those cannot replicate, and that's if we want to get nerdy, it's
Yeah.
activate
Mhm.
P21 and
Yeah.
activate P53 and prevent the sun cycle and all of that. Do you think that this dogma is wrong or it's still valid?
Well, potentially it's involved, but actually coming from the stem cell field, as we were building biomaterials for stem cells, we recognized that stem cells can either be actively proliferating or they can be differentiating, meaning becoming that tissue and making the matrix of the tissue. They couldn't really do both at the same time. So I think of senescent cells as differentiated cells in the sense that they're really active, signaling and talking to other cell types, saying that there's a problem. So, as people have looked at, for example, P16, the other sort of identifier of senescence, it seems to correlate with senescence, but it's not causative. So I'm not sure. And we've been looking at senescence in the tumor environment, and what we see in the context of immunotherapies, the new drugs that target the immune system, and certain cell types, certain tumor types that will not respond to the therapy, we see senescent cells around the tumor, and that's different than the tumor senescence itself, the cancer cell senescence. But in tumors that respond to immunotherapy, checkpoint blockade, we see senescence also, but it's a different type of senescence, and it has a wound healing phenotype. So I think we can actually connect wound healing tumor response to these therapies. It's been many decades that a paper came out in the New England Journal of Medicine characterizing tumors as a non-healing wound. So again, we get back to the wound healing. So senescence and wound healing and senescence and cancer definitely have a connection. And we're still trying to figure that out.
And if we're thinking about, I never thought about senescent as the differentiated cells. I thought about it like a terminal cells. So can you use the Yamanaka factor and basically move them back and then make a stem cell from a senescent, or nobody tried that?
Interesting idea. We've actually been playing around with senescence by a certain type of T cell we see inducing senescence, and then senescent cells can induce that T cell to become a certain way. The problem is we can't track what happens when we remove those factors, right? So I think we might be able to impact senescence by actually blocking certain immune cytokines.
If we think about a perhaps common condition that develops when you think about senescence with arthritis.
Yeah.
Do these senescent cells play a role in the development of arthritis in our joints?
Yeah, so that was one of our first studies in arthritis and senescence. And what we found was that after trauma to the joint, just like trauma to your skin or your muscle, senescent cells develop. The problem is, unlike other tissues like the muscle and the skin, where the senescence goes away. I don't know if they're removed or reversible. There's still a lot to figure out with that. Unfortunately, in the joint, which doesn't have the same blood supply and move cells and molecules, they accumulate and they don't get removed. And so you have a chronic inflammatory process that happens. And you also see that with aging and the age-related arthritis. So there are a lot of different types of arthritis. So, we don't know if they're connected to all the types of arthritis, but we definitely see in post-traumatic and some just age-related arthritis.
And the post-traumatic doesn't matter, if that's something that happens earlier in life, you still see that process happening later in life that it's much more significant.
Yeah, so we see younger animals still get that senescence development. It really doesn't matter the age. If it's already, and then you add and it really looks bad. So again, it's harder to repair and everything's worse with the older animals.
You mentioned the communication or interaction between the immune cells and the senescent cells,
Yes.
and it might be interacted or connected to the term infla-aging. So can you describe it a bit and explain to us a bit more in details?
Yeah, so there are a lot of different types of cells in the immune system that change with aging. First, you tend to be more skewed, so you lose T cells, which are an important immune cell component. So T cells are a target of those immunotherapies I mentioned, the checkpoint therapies, and they're important for your vaccine responses and for your memory of infections. And what we see is the naive T cells decrease with aging. right? So you can't mount as much of a response. And then your T cells that are actively secreting things, cytokines that are inflammatory, increase with age. So you see more of these CD8 T cells, you see more T cells that are really just active, making a lot of cytokines that frankly can be damaging. And what we saw in those old animals that had that pro-regenerative biomaterial, senescent cells were communicating with T cells very actively. Whereas in the young animals, there really wasn't communication between T cells and the senescent cells. So it's not even just who's there, it's who's talking to each other and whose conversations are the loudest, and sort of suppressing everything else that you might actually want in the repair process.
So it's similar to uncontrolled immune response, or maybe similar in a way to allergic reaction that happen in younger people.
It's different. It's a different profile than the allergic reaction, but it's a reaction that's promoting fibrosis,
Yeah.
and promoting that's actually used in certain infection responses. Like we're actually studying now how the aging microbiome might influence that, right? So, how much does if we take old microbiome and put moles, you can actually get some of that increased inflammation in the young animals. So it probably comes from a number of places, including the microbiome, diet, and actually also your history of infections. So we see memory T cells there that were responding to previous infections that actually infiltrate and impact tissue reconstruction.
Interesting. Very interesting. And that's in mice or in human?
So we see it in mice, and we're investigating it now around fibrosis and implants. So we're doing some extests that are around breast implants that induce that fibrosis, that encapsulates the materials, and we see T cells there that are known to be recognizing a lot of different things. Flu, Epstein-Barr virus, a number of different viruses. We can capture those T cells. So um, it's there's a lot to tease out there.
Right. Interesting. So one of your lab focus is working on the osteoarthritis. Can you explain what is that and why it is important?
Yeah, so osteoarthritis is was historically considered an arthritis of like wear and tear, right? So you're a lifelong runner and you hit a certain age and your knees just ache, right? So it's not the autoimmune type arthritis such as rheumatoid arthritis or psoriatic arthritis, but it was historically considered more mechanical in nature. What we're understanding now with it, in addition to the accumulation of senescent cells, at least in a model of post-traumatic osteoarthritis, is that there's also a residual immune inflammation. So it's not as inflamed or inflammatory as an autoimmune disease, but it's a low-level inflammation that over time the tissue will degrade and it can't repair itself.
And is that also caused in some extent by fibrosis that you mentioned on, you know,
Interesting.
materials?
Yeah, that's an interesting point. So it historically hasn't been considered fibrosis, but I think it has signatures of fibrosis, and it almost looks you lose the nice cartilage, and you get sort of this, yeah, I would say fibrotic looking like tissue. So I think so. That's not sort of the dogma of the field, but I think that's where we're at least leaning.
Interesting. And then joint replacements, are those typically replaced because of osteoarthritis?
Yes, yes. So there are a number of biological therapies that are being used. So there are things like stem cell injections, platelet-rich plasma. And there's painkiller, analgesics that you take to just reduce the pain. But those haven't really been shown to reestablish the structure. Um, but what's tricky about osteoarthritis, and in particular in the clinical trials, is that too bad. And then you could have cartilage that just looks terrible. It's all gone. They're not in much pain. So when you're designing a therapy in a clinical trial, what's your outcome? Is it reduced pain or is it the tissue structure or a combination of both? And so again, the diversity in people is, makes it a challenge to do the clinical trials that are needed to get it approved for broader use.
Sure.
And how do we know uh, what is a real pain, or it's more like psychological pain, or how can we make it more unbiased, let's say?
Well, there's certain um, there's certain molecules that are with pain, so we can look for those. So, my graduate student, former graduate student, who's now a professor in Korea, just published a paper on senescence and certain pain signaling pathways. So I think we are getting more of that. But again, that probably requires a biopsy or getting how will you test that is a little bit
Yeah.
tricky. But we're starting to understand the mechanisms. So I think that's at least a great start.
And that's definitely a big problem when we are living longer. And actually, all of us
Yes.
want to live better longer.
Yes.
And most of us will have some knee replacement or something like that. So it's something that unfortunately we'll have to have in our future. Uh, yeah.
Yes, and you think of the domino effect that if you have pain in your musculoskeletal system, your bones and your joints and muscles, then it's healthy, right? So it's an important cycle. And actually, people used to think that, oh, you shouldn't exercise or run very much when you have cartilage problems and osteoarthritis. Whereas, now recent studies show, well, actually the movement helps, right? You get your fluid exchange, get rid of inflammatory factors, and you can feel better. So, I think it's important to keep us moving.
Yeah, it's
That's a
interesting.
very that's a very interesting, yes,
Mhm.
a conclusion, because I have some joint pain, and because of that, I decided not to run. I'm cycling, but maybe I'll start running again. So thank you for that.
Well, both, it's
Yeah,
different modes to not
yeah,
overdo.
And it's interesting too that feeling more pain maybe does lead to people being less active, which can also impact some of those comorbidities
Yeah,
that can impact that replacement taking. It is a lot of connections.
it's all a system.
Well, for each of our guests, we always like to ask, with all of this knowledge that you have in your head, is there something as kind of a top tip or something that you do regularly and intentionally, um, that you do to improve your own longevity or maybe your own life health span,
Yeah.
your ability to stay active that you could share?
Well, it's really just the topic that we talked about exercise, right? And there are all these great studies on health span longevity, and really exercise is the only one that I see as being the most constant, reproducible, most significant effect across your body. So I was not the biggest exerciser in my younger years, with work and family. And now that my daughter's all grown up and as she got older, she actually got me into it. I started exercising more. So and enjoy participating in triathlons. So you get a little bit of a mix, right? So in addition
Okay.
to the biking and the running, you get some swimming too, which is good for the joints um, and also, particularly for women, but I know it's important for men too, is strength training, right? So keeping the muscle mass as the aging women is really important. And I like to eat well, so I don't know what more I can do than those
Yeah.
factors. Um, so that's where I spend my time.
And I love all of our guests have said things like exercise or trying to get on a varied diet, not necessarily focusing on the very specific compound that you should be increasing. So while there's lots of they're really the basics are what
Yes,
most people strongly encourage.
we can't get around it. There's not a pill for exercise, I'm afraid.
It'd be great if there was. It'd make a lot of money.
But come on, it's
Well,
great to get out, right? A part of doing those things is getting outside and getting in nature and being around people and community. So, yeah,
absolutely. Well, thank you so much for being with us today. It was really awesome to learn from you.
my pleasure. Thank you for having me.
Thank you so much.
And we look forward to exploring the research in the field of longevity each month with you and the leading scientists. For more information, please go to www.insighttracker.com/podcast. Thank you, Dr. Elisseeff.
Great. Thank you.
Thanks for listening to Longevity by Design. Please subscribe to this podcast on Apple, Spotify, or YouTube. Longevity by Design is powered by Insight Tracker, a personalized health optimization platform that helps people improve their lives by improving their bodies from the inside out using personalized, science-backed recommendations for nutrition, supplements, and lifestyle changes. To learn more, visit insighttracker.com/podcast.